Welcome to the Rich Report, a podcast with news and information on the world of big data. Today, my guest is from Pythian. We have Alex Gorbachev. He's the CTO of the company. So, Alex, welcome to the show today.
Thank you, Rich. Good to be here.
Yeah, thanks for coming on, Alex. So, I looked a little bit at your site. You guys have been doing, data consulting for a long time. But why don't we go through your slide deck and then we'll do a Q&A at the end.
Sounds good. Sounds good. Um, so starting with sort of who is Pythian, right? Well, we've been in business for more than 15 years, been servicing hundreds of companies. Traditionally, our realm was in a sort of relational database management, working with technologies like Oracle, SQL Server, MySQL, and etc. But recently, as we got into the big data world and it's become, it gained significant adoption in enterprises, we started working with technologies like MongoDB, Hadoop, Nitizen, and etc. So today I'm going to talk a bit about Hadoop as an introduction. So the next slide about Python, just to give you a better idea how we engage and who we work with. If you look at the companies today and you put the companies sort of on the chart depending on where they are in terms of data criticality, the more critical data for them, the more on the chart they're going to be to the right. You'll see that the more critical data is for the companies, the more significant is impact of an incident, being a data loss, being a security incident, a human error, etc. And also the strategic upside for the revenue from the data from this infrastructure running well is getting more significant. So at some point when companies sort of is crossing this love your data line, as we're calling, this is when the Pythian makes sense. While the rest of the offshoring industry is built sort of to hire average army of IT workers inexpensively, we are attracting the A team and the top skills. And the big data is yet another trend which contributes to this data concentration. So a little bit about myself. My name is Alex Gorbachev. I'm a CTO at Pythian. Been with the company for almost 7 years now. I'm a frequent blogger, very involved with the community, participate in multiple conferences, and work with the user groups as well. Director of a couple of user groups today. I'm also a champion of Big Data, which is a new program run by Cloudera, amongst another 12 members of this program, recognized as the champions of Big Data. Oracle ACE Director, which is a similar program that Oracle runs, recognizing community contributors, so very active in this area. So moving along, the idea for Hadoop, before I go into Hadoop, I'm not going to talk about big data much, but the idea is that, I work with some of the best engineers at Python, and given enough time and enough money invested, we can pretty much solve any problem with relational databases. However, more and more situations coming and more use cases coming where it may be way more expensive to use traditional relational technologies to solve certain data processing needs, and the newer technology as Hadoop becomes more, less expensive and more feasible for the business problems to solve. So moving to the sort of Hadoop principle slides. So Hadoop is based on on couple, I guess, key principles. One of them is bringing code to data. Traditionally, today, the code is significantly, like many order of magnitude times less than the data. So transferring data to the database servers, what traditional databases do, is becoming too expensive and is inefficient and difficult to scale. So bringing your code to the data, which sits on hundreds of nodes or on thousands of nodes, is much more effective, much more efficient. And another principle Hadoop adopted, which is not new in the industry, is a shared nothing architecture. So how does it do it? So a couple components that Hadoop has in a nutshell on this slide. We have Hadoop is based on the HDFS file system, Hadoop distributed file system, which is based on a white paper Google published a while ago in a Google file system, and that's basically an open source implementation of those ideas. And another core component of Hadoop is a MapReduce mechanism, which is also coming from Google. and it's an open source implementation of the MapReduce, which is basically a framework to run massively parallel jobs on large cluster of nodes. And those two technologies integrated well with each other. Now, having said that, there's enough Hadoop distributions that either don't use one of the Hadoop components and that don't use one of those frameworks. For example, the Amazon Elastic MapReduce uses S3 as the main permanent storage for files instead of HDFS, in using HDFS only for temporary files. So MapR, instead of using HDFS file system, they're using MapRFS. So HBase, for example, or Impala don't use MapReduce framework at all and run their own daemons processing data directly. So those are the two core components that Hadoop started with, but they don't have to be used in all the deployments or in all the data processing with Hadoop. HDFS architecture is, and that's a very simple view of it on the slide, is the following. There's only 4 data nodes in this diagram on the right that you can see. When you load the large files in the Hadoop cluster, and the Hadoop file system is designed to handle large files and not like millions or tens of millions of small files, when you load the files, they're split into very large chunks or blocks in Hadoop, and they are generally in size of 64 megabytes or more. And when each block is written, it makes it to one of the data nodes, then it will be mirrored to a second data node and a third data node, and that's all done in a sequential mode. So all in all, this operation of ingesting files in a Hadoop file system is actually not very fast. But those operations are very scalable because HDFS file system has quite a few limitations coming with it. So as each block is replicated on write, and as only one client can actually write to the file, and as each file can actually not be overwritten or updated, it can only be created and written to or appended later by a single process, by a single client. It makes it possible for hundreds or even 1,000 clients loading files concurrently at the same time without much synchronization. So it enables, and that enables very simple and very scalable architecture that is very simple to use, to build based on a very inexpensive servers, and that's why Hadoop clusters are generally built from very simple servers with a local storage only, reasonably inexpensive disks, even often without redundant networking, without redundant power supply, and etc. Simply because it cuts a lot of cost, and if one of the data nodes going down out of 100 or a few hundred or a few thousand, you don't really lose a very large amount of data, and the recovery from it is pretty quick and easy. So the key takeaway with HDFS is that as it's designed for the large to handle large amounts of data, it's designed also for scale. While sequential sort of data processing is not very fast in Hadoop, the fact that you can do many hundreds and thousands of operations concurrently without much concurrency issues is that what lets Hadoop scales. So, and when you start reading data, Hadoop works in such a way, and MapReduce mechanism works in such a way that local reads is basically the most efficient, and we'll see how the MapReduce framework is designed for that. HDFS design principles basically to simplify. It's a very simple file system. It's very specialized in how it handles the work and how it stores files, shared nothing architecture, and single-threaded writes. And this makes it very inexpensive to implement at scale and very scalable as well. Moving on to the MapReduce example, and I used in this example, I use example of a histogram calculation. Very often I see people use like a word counter or just counting a number of entries, which is less sort of usable example. So I think the histogram calculation would be a good example. So if you think about if you want to process website logs or other logs with showing response times, and there's a very large amount of those files, scanning them on a single machine may take very, very long time. So if you want to scale it on a, let's say, 100 nodes Hadoop cluster. When you ingest these log files, they will be split and stored on the hundreds nodes of this cluster. So when you send the MapReduce job to do the histogram calculation, Hadoop will schedule multiple map tasks per each node. And those map tasks will be working, the input data will be local on the node where they run. So here I showed you an example of like 4 nodes, and there's a 4 group of map tasks being scheduled in this way as an example. So each map will get its own slice, and they will be scheduled again in such a way that the mapper will read the slice locally, which is very efficient and very fast. And as mappers work, they read each entry in the log, and they will see the response time that is reported in this log, and they will basically output the bucket number, let's say the bucket number between 0 and 1 millisecond, and they will output the count of entry 1. And each map task may count thousands or a million of entries, and then produce the counts for each bucket. So when the mappers are done, the reduce jobs or reduce tasks will kick in, and they will pull from the output of the map tasks over the network, because reduced jobs may be running on different nodes where the map jobs were. They will pull all this data over the network and then basically calculate how many entries all mappers seen for each bucket that reducers produce, and they will basically output it. So the idea as an output files. So the idea is that map tasks are working with data and reading data as much as possible and producing as little as possible information data from map tasks that reducers then later on aggregate. And that's pretty much the whole MapReduce framework. So it's very simple. It's very scalable. If a node with a map tasks fail, the whole job doesn't fail. All Hadoop needs to do is to reschedule those map tasks somewhere on other nodes where the data is located, and it will be totally transparent to the user. So on the next slide, I list sort of MapReduce pros and cons. Again, very simple programming paradigm, very easy to learn, very flexible, scalable very well, excellent fit for the Hadoop file system because the mappers read locally. So as long as we distribute them where the data sit, using this sort of data affinity, then we can be very efficient. And it's fault tolerant, as I already explained. It's not with its own pitfalls, so it's not very efficient mechanism for many workloads, and it produces quite a lot of intermediate data sometimes, and the network can easily become a bottleneck if you don't design your MapReduce jobs very well. The complex manipulation require quite a few MapReduce jobs to be running one after each other. For example, if you think about a very simple select statement that you do in a relational database, which joins a couple tables and does some aggregations, it will translate in maybe half a dozen MapReduce jobs actually. And while each MapReduce job can process, a petabyte of data, it's actually not that fast on its own. So, only mappers in MapReduce leveraging the local reads. And as you've seen from the example, there's a lot of data that might need to be transferred between mappers and reducers. So there's some limitations in types of algorithms you can implement with MapReduce. And finally, writing MapReduce jobs, whether it's in Java or in another language, is actually quite a bit of coding efforts. And because of that, there were quite a few additional components. Moving to the next slide, quite a few additional components created in the Hadoop ecosystem. And when you talk about Hadoop, typically people talk about the whole ecosystem of Hadoop tools. So I'm giving you some of the examples of the most maybe important ones or the most common ones. The Hive as a component of Hadoop is basically a layer on top of Hadoop, on top of HDFS and MapReduce, which accepts the data manipulation language HiveQL, which is very much a SQL-like query language. And if you're already working with SQL, it will be very easy to work with it. It's not ANSYS SQL standard, but very close to it with select statements, where clauses, aggregations, and etc. So what Hive does is it takes these HiveQL queries, which are SQL-like, and basically generates a MapReduce job to process this data as the SQL would process in a relational database. And Hive also has a way to define where your data is and put basically table-like structure on top of it, whether it's a comma-separated files or some of the Hadoop-specific formats like Avro and etc. So, but in the end, Hive basically creates the same MapReduce job. So it actually can be pretty slow. Even on a small Hadoop cluster, run a very simple MapReduce job, processing very little data, takes at least 15 to 30 seconds, just because there is a lot of overhead of communication and scheduling the jobs and checking the status and etc. Another tool which is very commonly used is called Pig, and Pig is basically has its own language called Pig Latin, and this language is basically a language of manipulating data sets. If you worked with relational databases before, you know that relational database engines take your SQL and then they produce what's often called an execution plan, meaning basically how the relational database will go around fetching the data, merging those tables, joining the tables, grouping, sorting, and performing whatever you defined in SQL. So Pig, instead of defining SQL, let developer write in the language which reminds that sort of execution plan. For example, load this data set, sort it, load another data set, sort it, merge it together, group by a certain column, calculate certain average functions, and etc. So a slightly different approach to that. But again, what it does behind the scenes is generate a lot of MapReduce jobs which are then sent to Hadoop cluster and executed. A few other useful components that people generally use is Mahout, which is a machine learning libraries. That has nothing to do with SQL-like languages. In fact, they often run on a much less structured data or non-relationally structured data, and basically it's sort of a set of a black box component which let you run certain classification and clustering algorithms. So instead of implementing them yourself, you can pick existing classification, clustering, and other algorithms and run it on your data, like native Bayesian classifier as an example, and a bunch of other classifiers and clustering mechanisms. So Uzi is a workflow scheduler, which is basically let you schedule a pipeline of MapReduce job. If you, for example, want to implement your ETL framework, Uzi could then be used to orchestrate the whole data flow. And Scoop is a component which you will often see, which is used to transfer data between Hadoop and relational databases. Now, as you probably heard me saying multiple times, MapReduce is slow. It's like a total. It's very slow on its own, but if you run hundreds of those map tasks in parallel or thousands, then it's actually quite scalable and can process a very large amounts of data. So when people realize that MapReduce is actually not a very fast mechanism, they start creating a new components in Hadoop which don't use MapReduce at all. One of the oldest one is HBase, which is basically a NoSQL storage on top of HDFS file system without using MapReduce at all. Other examples which are more recent are things like Impala, which is basically take SQL-like, HiveQL-like language, which is, remember, SQL-like queries, and instead of producing a MapReduce jobs, it will use the Impala daemons, which are running on all the data nodes and do the data access pattern themselves. Very much like in any modern relational databases. And with this, instead of sending even the smallest queries and waiting for like 30 seconds to scan a row of 100, a table of 100 rows, Impala would make it in like half a second, for example. So this is when Hadoop gets into their realm of speed of thought analytics, something in a more interactive fashion that BI analysts are used to with relational data warehouses. Similar concept is Drill and Phoenix projects, which are run by different vendors. Hadoop is a commercial example of such implementation, which has been one of the longest on the market, which take ANSYS SQL and run it on top of Hadoop without MapReduce. Shark is another component on top of Hadoop, which is basically implements Spark and memory analytics on top of Hadoop cluster and lets you run Hive SQL on basically much faster than in using MapReduce. One of the recent entrants is Platfora, which is a commercial product, but it does a combination of in-memory analytics, basically in-memory cluster caching layer, and visualization and reporting tool, which looks incredibly slick. And if you work with a thing like Tableau in a relational realm, you will find Platfora delivering some of those interesting capabilities in a similar way. So moving to the Hadoop benefits slide. Hadoop is a very reliable solution to store large amounts of data for using unreliable and inexpensive hardware, and it's designed for a very large data file. What I didn't mention yet is that Hadoop changing our mindset, and in the past, if we load data in a large data warehouse, we will spend a lot of time designing it and structuring data correctly and just developing the ETL and data cleaning process. And after that, we can load the data. Hadoop is designed differently, and systems-based in Hadoop, you load data first, and then you structure it later. So it's a kind of different mindset, which is especially good when you do things like data exploration and etc., when you don't really know the structure that you need. Hadoop is designed to maximize throughput of large scans, right? Not sort of a response time-based solution generally. And it's leveraging parallelism and work at scale. And what's very important, it has a very large solution ecosystem. I only mentioned few tools out of 100 in Hadoop ecosystem, and it's very flexible development platform. Now, moving to the next slide. Hadoop doesn't come without limitations, of course. It is very scalable, but not very fast. And it requires a lot of assembly of different components. It's a very much do-it-yourself solution still today. There are commercial distributions that help you. Some of the integrations that help them to become a bit more enterprise-like. But a lot of instrumentation is missing still in the Hadoop. Commercial distributions are not free. The security is still very basic with Hadoop as well. So there are quite a few limitations that you expect to be solved in sort of enterprise database technologies, but Hadoop is still very young there and quickly evolving ecosystem. So the next slide will talk about how much does it cost. I'll just give you an example. What would it cost my company to start working with Hadoop? So in this case, if you look at things like, I look at building a 100 nodes Hadoop cluster using a Supermicro gear, which is sort of a second-tier enterprise hardware, and I choose to do it as cheap as possible, meaning you order all the components you could separately, put the things together yourself, and end up with such configuration. So if you build a 100 data nodes cluster with about 3 racks worth of hardware, almost 1,000 CPU cores, more than 6 terabytes of RAM, and 400 terabytes of usable space after all the triple mirroring, it will only cost you $300,000. So it's reasonably affordable to store 400 terabytes of data, and not only store them, but having a huge processing capacity to work with the data. Again, it's almost 1,000 CPU cores in this cluster. Just to give you an example of what it is, what it would cost to enter. So my last slide, I want to kind of get to the point is if I would put Hadoop next to relational database, what would it be like? How would they compare to each other? So as I already mentioned, load first, structure later is Hadoop approach versus structure first and load later. Hadoop is reliant on cheap hardware. Doesn't have to be an enterprise-grade hardware, and it's very much do-it-yourself platform as opposed to full of repeatable solutions where relational databases excel. It's much more flexible data store in Hadoop as opposed to more efficient data store. When the processing is very efficient, Hadoop takes it by Hadoop achieves effectiveness by scale rather than by efficiency as the relational databases do. Obviously, the data sizes, when we talk about Hadoop, we're talking about, petabyte scale, maybe hundreds of terabytes, and relational databases is terabytes, maybe tens of terabytes. And the size of clusters is obviously order of magnitude different in Hadoop versus relational databases. And that sort of rounds up my introduction to Hadoop. And Rich, if you have any questions, that'd be a good time.
Yeah, yeah. Thanks for that, Alex. It's really helpful. I hear a lot of these terms batted around, and you put a great kind of a wide perspective on things. I wanted to ask you about some developments coming up with Hadoop, Hadoop 2.0, and they're going to be incorporating this Apache Yarn. And could you comment on how is that going to change how your clients approach the data?
Right. The Yarn is still a little bit young at this point to use in production for most of the clients, and I think pretty much all Hadoop distribution vendors agree on that. What Yarn gives is that Yarn gives a flexibility of having multiple components running on the same Hadoop cluster in a very friendly way. That I think the best sort of the biggest advantage that Yarn gives to the clients. Now, if you think about this in this way, imagine that you're running a Hadoop cluster where you have HBase when you run Impala, which is non-MapReduce based sort of SQL analytical language or component, as well as running Hive and Peak jobs and etc. Currently, there's no way to allocate resources to each of those components in a friendly fashion. You'll have to configure them and allocate resources in such a way that they don't sort of step on each other's toes, right? But in this case, you underutilize your capacity. If there's not enough MapReduce workload, you don't want your Impala daemons taking advantage of that unused memory or unused processing capacity. So, and Yarn will make it easier for when tools start support and integrate with Yarn. It will make easier and simplify those resource management. Also in Hadoop 2.0, the MapReduce, new MapReduce 2.0 coming along, which has more enhancement and into the MapReduce framework, which allows better produce less temporary data, for example, between mappers and reducers as much as possible, and trying to reduce amount of data sent over network and etc. So adding some additional efficiency to the basic MapReduce framework that I introduced.
And good, Alex. So I wanted to ask you about security, right? Especially when we're comparing things to relational databases, which have that long history and hardening. Is security something that you see as an obstacle to Hadoop in the enterprise, or what are your thoughts there?
Definitely, deployment of Hadoop. There's two aspects of it. The one aspect of it is since the platform itself was rather new and didn't really have security in mind when it was sort of developed, and I believe you had a recent podcast which was specifically focused around security, so your audience would probably go there for more details if they want to, right?
Yeah.
But it's obviously preventing Hadoop from entering in some of the more enterprise deployments, and that's where there some of the vendors like Cloudera and Map are recognized and start adding additional security features on top of Hadoop. Intel jumped on it as well and added some additional security features into the Intel distributions as well. But that's only, I think, one side of things. Another side of things is that Hadoop makes people integrating a lot of data from different data sources together. And when this data is processed together, that's what makes sort of a big data platforms powerful. I think the industry, the analysts start calling it as a sort of data reservoirs. And what happens is that you mix the data, which has a different security regimes, which has a different, criticality and different, access levels, and you put all of this together. And if you start granular control access to the data, you're losing this ability to process the data together.
Yeah.
So it's a kind of catch. It's a kind of a two-edged sword, right? You want this data to give to analysts together at the same time. By doing that, you're violating some of the potential, security, access levels that different data sets have. So it is a difficult situation, but it's more difficult from business perspective rather than technology perspective. Technology catching up quickly, and it'll be there very soon. Already there. It's just not as easy as in relational databases coming with
Yeah.
right? But it's possible. But I think the biggest problem with this, as the big data become more and more mainstream in the enterprises, the biggest problem is how do companies solve this problem from business perspective.
hmm And kind of a wrap-up question here, Alex. Working with Oracle as a partner, do you think the Oracle company sees this Hadoop as a threat or as an opportunity?
Well, it's definitely an opportunity. I mean, the short terms, what we see is that Hadoop is more deployed these days in enterprises as a sort of a helper, for example, helper in a data warehousing. When Hadoop becomes the platform where their ETL process is going to, as a transformational platform, which integrates lots of data sources, cleaning them up, and then when data is cleaned up and transformed, loaded into the data warehouses, right? So it takes that space, or it takes a space of archival platform when the data becomes too old to store in a data warehouse, but the companies don't want to purchase completely, they move it to Hadoop, right? So it's solving sort of reducing cost of operating cost of those environments. And another, I think, aspect of Hadoop deployments is when you deploy it as more of a top-line contributors, when it enables new products, when and adds more revenue due to insights in your customer behavior, and etc. And as more and more customers get into Hadoop and get to know it, they become more advanced users of Hadoop when they become not just a secondary system, but becomes more sort of a primary system.
Interesting.
I don't know if that sort of answers sort of your question.
Yeah. That's helpful. Well, Alex, this has been terrific. I want to thank you once again for coming on the show today.
Thank you, Rich. Good to be here.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on the world of big data.